The objectives of this paper are to summarize current approaches to technical and physical conservation and to establish whether more specialized approaches are needed to conserve modern architecture. As you know, our aim during this two-day meeting is to outline the most pressing needs and to address areas of conservation requiring our attention. We must suggest options that may be most viable for practitioners to advance the field. As part of this essay, will also provide a context for the case study presented by Wessel de Jonge and Miriam Boeshu that will complement this essay in a more specific perspective. The essay, together with the case studies, will provide a basis for a focused discussion tomorrow on the identifying the key areas of conservation requiring our attention. Since the early part of the 20th century, a key theme in the development of modernism was the determination to design and erect buildings that sought to accommodate rapid growth in society. Post-war construction in cities like Le Havre, France, built in the late 1940s and 50s, were part of a full-scale reconstruction of towns which were nearly entirely destroyed during the war. The reconstruction of the city of Le Havre was designed by chief architect Auguste Perret, the teacher and mentor to the Swiss architect Le Corbusier. Monument architecture of the 20th century, constructed in reinforced concrete at the Church of Saint-Joseph, served to memorialize and pay tribute to the 5,000 civilians who died in the conflict. Modernist buildings embraced the spirit of industrialization, both in a quest for new architectural expression and in a search for affordability through customization based on specific design for unique purposes. While modern architecture sought to break from the past by embracing new technology, the results were that building structures were quite different from traditional building types. Architects and the construction industry also collaborated to create a new aesthetic, which integrated specific design intent carried out through new building techniques and innovative materials. They sought to achieve maximum functional efficiency by lowering costs while increasing production volumes over very short spans of time. Today, we are faced with a multitude of buildings that were constructed during this era, which may require repair and maintenance. We are in a constant reactive mode as we try to balance new technological standards aimed at improving their performance while addressing comfort issues and environmental goals. This presentation examines the current state of physical conservation and presumes that there is really no methodological difference in the approach to conserving modern architecture as compared with traditional practice. However, given the shorter lifespan of building materials and their performance over time, it is assumed that a more frequent monitoring and maintenance is certainly required in order to sustain these buildings from this era over time. In addition, knowledge and understanding of the 20th century building design, detailing, and an understanding of material lifespans is required if appropriate measures can be taken to ensure added long-term survival and integrity of the building fabric. Looking at the current state of physical conservation, we face modern buildings that require repair. We must balance new technological standards at improving their building performance. While heritage of the recent past has performed its intended program function for the last 50 years, technology has often become obsolete, while building standards become more stringent. Many building materials and systems of this era have reached the end of their physical and economic lifespan and require repair or replacement at the very least. Most often, they are in great need of care and maintenance to sustain them. Today, most buildings are constructed from a multitude of materials. each with a very specific functional demand and complex assembly requirements. For instance, an exterior wall assembly contains materials that keep out the rain and wind and air infiltration. They are thermally insulated, and inhabitants can be protected from exterior temperatures. They are structurally supported, and they support the exterior envelope system. One of the most important questions raised by architects from this era was the ways in which the building's design should respond to the rapid changes in society. Two different principles and approaches arose based on the customization required in anticipation of program functions. Buildings could be clearly understood on the basis of their distinction between whether they were functional or rational. Zonnestrahl Sanatorium was designed by the architect Jan Duker between 1926 and 1931 and is recognized as one of the icons of the functionalist architecture movement. Zonnestrahl was intended to last only as long as necessary to eliminate tuberculosis, an estimate of 30 years. For this reason, the sanatorium was built of industrial products and used construction techniques of dry assembly of prefabricated building components used in smaller quantities than in the needs that were traditionally used. The building envelope was quite thin, delicate, and streamlined. The case study on Zonnestrahl Sanatorium, Building Technology Systems and Conservations that Wessel will present at the colloquium demonstrates a functionalist approach to building design and its resulting typology and the physical conservation challenges unique to this type of structure. However, more than any other material, concrete, whether reinforced, pre-stressed, cast in place, or precast, was widely used and the most symbolic of architecture of the modern movement. The somber interior of Saint Joseph Church in Le Havre, constructed of the cast in place concrete in the neo-Gothic style, is 107 meters tall and acts as a beacon visible from out of the Sea of Normandy. The case study from the Laboratoire de Recherche des Monuments Historiques on concrete technology and conservation, to be presented by Myriam Bouchou, provides context for ongoing research on historic concrete, identifies research questions, and discusses how these questions were addressed through the development of physical conservation strategies for key monuments designed by Auguste Perret, Le Corbusier, and others. Many materials and products were typically manufactured using mechanized and large-scale processes that were often based on patented material properties and production formulas. Composite materials also included intricate metal alloys like stainless steel, weathering steel, and Monel metals, as well as complex plastics and synthetics. The gateway arch, designed in 1947 by Finnish-American architect Eero Saarinen and German-American structural engineer Halskaro Bandel, is the centerpiece of the Jefferson National Expansion Memorial in St. Louis, Missouri. Here, the exterior skin of the gateway arch in St. Louis, Missouri is constructed and clad with sheets of stainless steel that are welded together as shown in this image. As with the case of the arch, modern materials age over time, but in many cases, they were intended to retain a pristine, non-weathered appearance. Conservation of modern materials like metals requires resolution of the issue of newness and patina. This topic has been a focus of discussion for over 2 decades, and yet the questions remain in particular to conservation of metallic and alloy surfaces. How should these materials be treated and whether to a like-new appearance? When does this approach conflict with traditional conservation approaches? More case study and research work on the conservation of modern metals should be made available, re-engaging metallurgists with a number of the manufacturers to find ways to develop finished treatments for metals, including aluminum and other types of alloys. The visual impact of modern movement architecture also depends on the impressions of lightness, thinness, and minimalist aesthetic that could be attained through new building construction attributed to advance in newer skeletal load-bearing frames. At the Haus Schminke by Hans Scharoun in Lubau, Germany, the load-bearing function is reduced, and interior spaces could be made more fine-tuned to the specific performance requirements in terms of functionality and even with regards to interior climates utilized through building physics analysis. The approach was primarily attributed to the desire to regulate daylighting and implement ventilation controls. By contrast, with the modern movement sought to achieve a pristine and more formal aesthetic clarity that lacks surface relief, conventional detailing, and sill edges, drips, as well as sloped roofs and copings. These were all lacking. This created a myriad of problems over time, as the materials were more exposed and vulnerable. This aesthetic contributed to air and water infiltration problems related to delicate thermal detailing of the building envelope, with little to no redundancy, allowing air and water migration in through its thin skin. The study of building envelope, including the evaluation, performance, and the lifespan studies of building materials, has long been considered to be a discipline that paralleled the modern movement. Building envelope diagnostics and the use of building physics has been recognized as an essential discipline that provides necessary tools for examination and the understanding of responses to climate. It has allowed us to appreciate that the early pioneers were aiming to achieve through the use of thin-skin technologies. In many ways, the current debate on sustainability is not so much different from the public health debate of the 1920s. While the focus has shifted from then to now, examination through the lens of building physics can be further utilized in the holistic stewardship of modern heritage, in that a sound understanding of this field of research and practice would support the evolution of the conservation of modern architecture at this stage. Research on environmental monitoring and on climate control systems and the conservation of modern buildings should be targeted to identify more synergies with the discipline of building physics to advance this area of practice. Developed as early as 1918, the Bauphysics, or building physics, made available literature and research at that time by companies specializing in the heating industry and examining the climate performance and the improvement of interior building environments. As an essential discipline today, the examination and understanding of climates and environmental monitoring further facilitates the stewardship of our heritage. While knowledge of building physics and standards is in development in the conservation of modern heritage, sound understanding of this field of research and practice would support the evolution of practice. Physical conservation of buildings often requires an investigative approach as well. This needs to occur to identify the building's structural and cladding systems, the integral materiality and methods of assembly, as well as potential mechanisms for deterioration. Given the variety of building systems and components utilized over the last century that did not have a proven record of performance, increased attention to building pathology and diagnostics is also rudiment if we are to identify and respond to inherent failure mechanisms that are part of the building assembly. This approach often entails a multidisciplinary approach and is key to better understanding of the past and current performance of the building envelope system. However, in order to monitor and investigate building deficiencies and to respond with appropriate solutions, we need to develop more diagnostic tools and non-destructive methods of investigations that would enable us to better identify inherent problems in the building systems. This would enable better conservation strategies and maintenance in the near future. However, responding to building failures is challenging, especially when there's an inherent deficiency in the modern building system and materials, which may cause failure that is integral to the detailed assembly. In some cases, traditional repair approaches, such as in-kind replacement of the original building fabric and detailing, may lead to repeated or continued failure in a building system. The consequences of this related to this approach can be very problematic. In the case of the Amoco building from the Standard Oil in Chicago, designed by Edward Durrell Stone and completed in 1974, the 80-story structure originally clad with Carrara marble remains a noteworthy example of a modern high-rise that not only experienced material failure due to exhibited weakening signs of panel bowing, but the original marble panels had to be replaced with new light-colored granite panels to match the original ones. Here, the decision to maintain the aesthetic integrity, which improved building performance, was selected over in-kind replacement, which would have built in the identified inherent material mechanism of weakening marble panels when exposed to weathering in this particular harsh cyclic freeze-thaw environment. It is important to recall that this large-scale material failure occurred just 15 years after the completion of the building. It provided an understanding of how similar materials can perform over time, and that material properties and their weathering processes should be factored into the design of the repair to promote a continued life and long-term conservation of the building in its envelope. The importance of understanding historical constructions by their building typology with knowledge and understanding on the type of prefabricated building materials and systems is also essential in considering the long-term conservation strategy. One of Mies's final commissions, the School of Social Service Administration, completed in 1965, is a one-story steel and glass pavilion in the heart of University of Chicago. The building, which occupies a busy corner, has been in continuous use for half a century as an office and teaching facility. While it had undergone basic maintenance over the years, detailed attention to problems related to extensive corrosion of the building's steel frame, including glass failure from normal temperature expansion and contraction, had not been addressed. The importance of understanding historical constructions that may be categorized by functionalist building typology through the use of prefabricated building materials is vital when determining appropriate conservation strategies. Buildings that are made of these materials that have repeated very low tolerances, such as modern steel or aluminum curtain walls, require rigorous identification and documentation of their assemblies in order to have a thorough understanding of its building design. The Social Service Administration building at the University of Chicago by Mies is constructed using large steel frames and huge expanses of glass, so characteristic of his work, which served to make less of a barrier between the outside and inside of the building. Mies's choice of this system, as with many of his designs, makes conservation challenging due to a very limited tolerance and inherent issues with the envelope as built and constructed. The successful basis for sound conservation practice here assumed that the traditional approach may also not be suitable to properly maintain overall integrity of the building system and its material components. While a balance to retain as much of the material fabric was maintained, successful repair of the exterior envelope relied on a requirement to dismantle the entire curtain wall and incorporated new laminate glass that was thicker than the original into the original framing system. In order to address the lack of redundancy of the thin-skinned building envelope, together with new building code requirements of the university, the steel window frames and sash were disassembled, repaired, and repainted, and fitted with new laminated glass on site to meet safety requirements. By direct comparison, the Farnsworth House, designed by Mies in 1951, now owned by the National Trust for Historic Preservation, awaits a similar conservation program to stabilize the deteriorating steel frame and sash of the plate glass window system. Similar to the SSA building, a full-scale disassembly to peel back material layers may be required to repair the original steel frame components of the window wall system. It is important to learn from how we have dealt with similar issues in the past. Guidance is needed on how to identify the vulnerabilities and how to diagnose these problems. However, it is also important to communicate methodologies to new audiences who also assist to advance the field. We should consider how case studies on examination of the vulnerabilities could aid in demonstrating how others have managed to balance some of the philosophical issues with the physical conservation challenges. Some of the conservation challenges at the Whitney Museum of Art on the Upper East Side of Manhattan were with the stepped cantilever front facade designed by Marcel Breuer in 1964. Here, the exterior building cladding consists mainly of 3-foot by 5-foot, 2-inch thick panels, saw cut from black granite dimension stone. In this project, while the cladding support angles and anchors were stainless steel, the anchor inserts cast into the concrete wall substrate were bronze. What can be seen here is that the common mild steel nuts, bolts, and washers and shims were used as the attachment hardware. This caused a gradual corrosion of the steel hardware due to galvanic action that continued without discovery for almost 30 years. During the investigative process, the historic archive was utilized to obtain critical as-built documentation of the original attachment details, which provided information on how to develop a scope for conservation and repair. All of the granite panel locations and conditions were documented, and the panels were removed, cleaned, and temporarily stored on site. Eventually, they were all reinstated with new connection hardware and fixings, but the original stone and all of the cladding was retained. Looking at building maintenance and conservation, there are a number of questions that come to mind. Is there any other approach to the conservation of these building types? Are there any inherent building assemblies and materials which could be considered for preventive maintenance that could support longer lifespan to these existing components? Can the rate of an inevitable deterioration of these buildings assemblies be regulated through routine maintenance? The physical conservation of modern buildings shares the same approach as the conservation of traditional ones. Because of the advances of thin-skin construction using prefabricated building components and skeletal frame buildings, the challenge is that more frequent monitoring and maintenance is required to maintain the shorter lifespan of these materials. Additionally, training in building pathology, investigative techniques, and non-destructive testing to more fully understand and evaluate the multitude of conditions in these building types is needed. Through a successful promotion of long-term building performance and sustainability, the use of building science could also provide insight into material life cycles as well as improvements in climatic conditions. The colloquium is meant to build on these issues. While additional technical information and publications on successful solutions for repair and conservation to modern buildings is useful, we need to target practitioners and consider building physics as part of environmental monitoring for modern buildings. Currently, what do we need to learn to obtain better conservation results from modern buildings? Here are some of the key issues that we have outlined in the paper. While much of the useful information has been learned and made available on the conservation of modern architecture, I would like to argue more knowledge is needed to better provide useful tools in the integration of long-term care of modern heritage. Thank you.